Good afternoon, class. Today our lesson is it only natural? And we're going to be learning about climate and some of the various factors that affect climate. I want to start by asking you a question. Does anybody know what a budget is? Who can tell me what a budget is? I think your hand was up first.
A budget is when you note how much you can really spend out of your check or your salary.
Keeping track of how much you're spending each month out of your salary.
Or to save money to know what you want to buy and save up for.
Right. Saving up for things that you might want to buy. So you're keeping track of how much money is coming in and how much money is going out. So, for example, here's a scale, okay? So if I want to keep track of how much money is coming in, I've got this much money coming in. If I want to have a balanced budget, then I want to try to get it equal. It's not quite equal. I've got a little bit more money coming in than going out, so that's probably a good thing, right? And in nature, believe it or not, there's budgets in nature. And one of the things in nature that we want to talk about budgeting is the amount of sun's energy coming in, the radiant energy. How much sun's energy is coming in and hitting the earth? Now, do you think we want to have about an equal amount of radiant energy coming into the earth's atmosphere and leaving? Or do we want an imbalance? What do you think's happening?
I believe we want a balanced one because with radiant energy, you would want it to be kind of balanced. You wouldn't want too much heat coming into the earth, but you wouldn't want too much heat leaving us.
What might happen if there was too much radiant energy leaving? What would happen to the earth? What would happen to the earth? What do you think?
I think that the earth would become, it would be another ice age and become slow.
Perfect. He said it would become another ice age. The Earth's atmosphere, the Earth would get colder. And if you look at the Earth's history over time, we've had about 5 ice ages over time where the Earth's gotten cold due to various factors that we're going to learn about in a little while. So that's good. And what if too much of the solar energy, that radiant energy from the sun, is getting trapped inside the atmosphere? What's going to happen to the Earth then?
It's like we're going to have too much heat and we'll be a lot warmer and hotter.
Right, it's going to get too hot for us. And that might not be so good for us, for the plants, for the ocean. Maybe temperatures are getting too warm, for aquatic life in the oceans and rivers. So we don't want it too hot, we don't want it too cold. We want a nice balance. Okay? James, would you review some of our key vocabulary that we're going to need to know for our activity today?
I most certainly will. And there were quite a few things that you guys mentioned just now when you were having that discussion, and you've already defined many of the terms that we have up here on the board. The first term, radiant energy. Can someone read that for me? Yes, ma'am.
Energy that travels by waves or particles.
And radiant energy, we talked about this idea of Earth receiving radiant energy and trying to keep that balance of the radiant energy that comes in and goes out. When that is not balanced, and someone mentioned something about, I think it was you, the question was asked, what happens when we have too much radiant energy that's trapped in the atmosphere? This happens. Can someone read that for me? Yes, sir.
Long-term increase in Earth's average temperature.
Global climate change is when you have a long-term increase in the temperature of Earth. Another thing that I want to talk about very quickly is the greenhouse effect. Once again, we talk about this idea of what happens when radiant energy is caught in the Earth's atmosphere. And that leads to, on a count of 3, we're going to read this. 1, 2, 3.
Greenhouse effect.
Give me one person nice and loud who can read that for me. Yes, sir.
The atmosphere of a planet traps radiation emitted by the sun.
What happens in the greenhouse effect? We have certain gases. Well, somebody read this for me, greenhouse gas. Someone I have yet to hear from. Yes, ma'am.
Any of the atmospheric gases that contribute to the greenhouse effect, including carbon dioxide, methane, nitrous oxide.
Excellent. And one thing I left off, water vapor is also a part of that. When you have too much CO2 in the atmosphere, it gets trapped, and that leads to the greenhouse effect. Can someone tell me from looking at the board, in your own words, the difference between climate and weather? We hear those terms all the time. Well, I'll tell you what, we've read that already. So if I was talking about the weather or the temperature of Washington, D.C. back in 1930s, would I be talking about climate or am I talking about weather? Back in the 1930s, yes, ma'am.
You'll be talking about climate
I'm talking about climate. Why?
because it happens over a long
Over a long time period. So we've defined all of these, and I think we are good to go. Yes.
So now we're going to do an activity where you're going to learn about some of the natural causes of climate fluctuations and why some years it's warmer and colder than others. So I'm going to hand you each one of these. We can pass these, take one and pass them around, okay? And I'll explain to you what we're going to do. So there's 6 stations, one at each of the 6 tables. All of the number ones will start at station number 1. If you counted off and you were a 2, you'll start at station 2, etc., station 3, 4, 5, and 6. But basically what you're going to do is read the card at the station and follow the directions. Move to your starting station, depending on what number you are. The first one is Earth's Wobble, and what you're going to do here is take the top and spin it, and as it moves around the tabletop, I want you to notice what's happening. Does the top's handle point in the same direction the whole time, or does the axis change? And then you'll record your observations on your sheet. So station number 2 is Earth's orbit. And what we're going to do here, for each illustration, I want you to take your centimeter ruler and I want you to measure the distance between the point in the center of the sun and each of the black dots on the Earth as it's traveling around the sun. And we'll do that for what it was like 95,000 years ago and what it's like today. And then you'll record your measurements on your student worksheet. So this one is station number 3, the tilt of the Earth's axis. And for here, we're going to find 30-degree north line on the globe, and we're going to shine the flashlight on that spot. First, you're going to record what part of the Earth, the northern hemisphere, the southern hemisphere, is getting the most direct sunlight. Then you're going to keep that flashlight shining in the exact same spot that you were, and the other person's going to put a wedge and tilt the globe a little further away. And then you're going to observe where it's hitting. And then you're going to put the half-inch wedge on the other side, and you're going to observe where the most direct sunlight is hitting the Earth. So this is station number 4, volcanic activity. So for this one, we're going to simulate all of the ash and dirt and things that are spewed up into the air from a volcano. So we're going to simulate the ash coming up from the volcano by using clear piece of plastic and a mirror. So if you can go ahead and shine the flashlight here, what's happening? Do you see the sunlight coming through the plastic? Yeah, most of it's going through. Very little is getting deflected back. So this is a period of no volcanic activity. Now let's pretend a big volcano erupted in Hawaii, and there's ash in the atmosphere kind of creating this dark cloud. Is the sunlight able to get through to her? Is it going through the shirt, or is that sunlight bouncing back? Bouncing back. So less sunlight is able to penetrate through. So this is station number 5, and this is changes in the sun's output. So the sun doesn't always give off the exact amount of radiant energy all the time. Sometimes there's little flickers or sunspots, and there's flares and it's giving off more energy, and at other times it might be giving off a little bit less energy. So this candle, this flickering candle in here, is supposed to represent the sunspots coming on and off. And what I want you to do is observe it for about a minute, and you can even put your hand up near it and see when it's flickering on, does it feel hotter? When it's off, does it feel cooler, and what's happening? And then go ahead and record your observations on your student sheet. So this is station number 6, the greenhouse effect. And what we're going to look at here is the sun's energy coming down onto the Earth, and some of it's getting trapped. So how we're illustrating that is, for this one, here's our Earth. We've got our soil in the bottom. We have our thermometer taped inside. Only half of it is covered. So this would be the greenhouse gases only getting partially trapped. Some of them are able to escape. We're going to record what our temperature is on your student page here, and we're going to compare it to this one where the entire Earth, we're simulating here, with plastic wrap over the entire thing. The heat from the sun, our lamp here, is getting trapped inside and it can't escape. So you're going to take a look at the thermometer inside the bottle and see if it's hotter or cooler in one versus the other, and then you can record your observations on your student page. All right, so now that you've visited all 6 stations, we're just going to discuss a little bit about what was happening at each of the stations. So at station number 1, we were talking about the wobble effect. So the tilt of the Earth, and sometimes the Earth wobbles just a little bit. Now, is the amount of sunlight hitting the Earth, is it changing because of the wobble? No, it's not actually changing. It doesn't affect the total amount of solar energy received by the Earth, but it does affect which parts of the Earth are receiving the most of that solar radiant energy. And then at station number 2, that was when we talked about the orbit of the Earth. So sometimes the orbit of the Earth is more like a circle, and sometimes it's more like an oval. So if we have our sun here, sometimes it's more of an oval, and sometimes it's more like a circle where the Earth is the same distance from the sun pretty much at all points. But in periods of geologic time, over long periods of time, it's a little bit closer here and a little bit further away. So when the Earth is farther from the sun, do you think it's going to be warmer or cooler during those periods? Cooler when the Earth is further away. And it takes about, like, 95,000 years for that to change. So not in our lifetime. Then at station number 3, we were looking at the tilt of the Earth, because the tilt of the Earth changes. So when the United States is tilted a little further from the direct sunlight, during those periods where the tilt of the Earth has changed a little bit, we're going to have more severe seasons. Summer's going to be hotter, winter is going to be colder than normal. So station number 4 was our volcanic activity. So what did you observe when you shone the flashlight on it?
When I shined the flashlight on the plastic, we realized that the light of the flashlight will go through the plastic, and on the mirror, the flashlight will reflect off.
If the sun's energy is being reflected back because there's a lot of volcanic ash, if that sunlight's, more of it's being reflected back, is the Earth going to get warmer or colder if some of that solar radiation is reflecting back off the ash?
Cooler.
What did you observe here with the candle flickering? If it's flickering on and there's like a flare of energy from the sun, how's that going to affect the Earth's climate?
Warmer.
So station number 6 was our greenhouse effect that we were modeling. And if we have a lot of carbon dioxide in the atmosphere and other greenhouse gases, what's going to happen if they're trapped inside our atmosphere and they can't escape? Is it going to get warmer on Earth, or is it going to be cooler?
It's going to get warmer.
Great, that's right. So now I'm going to hand out the causes of climate change. This is a graph, and I want you to take a look at it because it's going to show you a graph of recorded temperature over time from the 1900s into the 2000s to present day. And I want you to take a look at what's happening to the temperature over time. And it also is going to show you variations in the temperature over time due to natural causes, like we just learned about at 5 out of the 6 stations. The greenhouse gas was more of a human effect. And then the other color is going to show you natural and human effects. And I want you to take a look at the graph and think about what trends you're seeing. And we'll talk about that in a minute. So we'll go ahead and pass these out. So if you look at your graph, what can you tell me about natural factors only affecting variations in the climate?
It's fluctuating during the years. It started going down from where it originally started, unlike natural and human factors where it started to affect by gaining. Going up by the years, it started becoming more and more, affecting us even more.
So what are you hearing about Earth's climate today? Are we staying the same? Is it getting warmer? Is it getting colder? What are you hearing in the news about Earth's climate today? You hear that it's getting warmer. And this graph sort of separates the natural causes for natural fluctuations versus humans' effect.
Now, we talked about this idea of the different greenhouse gases that cause global warming. This is an illustration of the air that we breathe. If I look at this color, the green is going to be what? And the blue is going to be? So just based off that pie graph, if you had to give a number, assign a percentage to the nitrogen that's in air typically, what percentage would that be?
75%.
75, that was pretty good. Give me up a little bit more.
80.
Down a little bit more.
78.
78%. Typically, the air that we breathe is 78% nitrogen. So if I look at oxygen based off that pie graph, what percentage do you think oxygen would be?
22.
22, lower.
15.
And actually, it's 20.9. So if I were to round up, that would be what? About 21%. And this little small slice would be carbon dioxide, argon, and other gases. To give you an idea of the harmful effects of CO2, I give CO2 meters to schools. If you are ever inside of a building, anytime you go beyond 1,000 parts per million CO2, that's when you are in the dangerous range. And we do have a school that was able to mitigate their CO2 by using plant species. Plants can bring down CO2. Another thing I want to talk about very quickly is the Mauna Loa data sheet. I'm not going to pass this out, but there's a location in Hawaii where they measure the atmospheric CO2 that's present on Earth. They've done this for the past 70 years. Over the last 2 years, they have gotten the highest readings ever of CO2. Ms. Sherry was talking about the idea of natural causes in terms of temperatures rising and things that happen to the Earth. We also have things that are man-made, and a lot of that is based off man-made things that we are doing.
Does anybody know what some of those things are that can contribute to the rise in carbon dioxide levels? We see a lot of it on the streets out here when we're going from place to place. Cars? Uh-huh. Buses. And what about how we warm our schools and houses? We're burning fossil fuels, and that contributes a lot to increased carbon dioxide levels.
Let's continue this outside.
But one thing we want to do with this lesson, and tomorrow what we're going to do is we're going to actually do some research on the internet, and we're going to try to gather some data on carbon dioxide levels over the past 100 years. I want you all to collect the data. We're going to make sure that we're using good sources. Then you're going to graph the data. You're going to each create your own graphs and posters. We're going to put them around the classroom, and we're going to share that information. Because as good scientists, we want to make sure that what we're researching is from good sources. We want to make sure that we have accurate data so that when we're talking about these things, we have the science to back it up. So then once you do your graphs, I want you to decide what trends do we see in the graphs, what's been happening to carbon dioxide levels, and how has the temperature been changing, records of climate over the past 100 years. Is there any correlation? Is there any connection between the amount of CO2 in the atmosphere and the average temperature of a typical location over the past 100 years? And see if you see any correlations, see if you see any trends. Then I want you to construct a statement. I want you to make a claim, use the data that you've gathered to back it up, and then you can have a little debate as to what you think carbon dioxide levels in the atmosphere have been doing over the past 100 years and what that means to our climate now and what it might mean to our climate in 20 years, 50 years, or 100 years. So we'll tackle that tomorrow. Ms. Dawson, anything else you want to add for the students to work on tomorrow or think about?
So while they're doing their graph, basically what would it look like in the future, and what could you do differently now to impact with that vision, or how it should look in the future. So basically taking steps now for tomorrow.